Now that we understand what an atom looks like, mostly empty space with a positively charged nucleus composed of protons and neutrons, held together by the strong nuclear force, surrounded by electrons occupying a region of probability and attracted to the nucleus by an electric force. Yeah, now that we know that, we can talk about elements. When a bunch of the same atoms bond together, an element is formed. An element cannot be broken down further by a chemical reaction. This chunk of charcoal is a bunch of carbon atoms bonded together. There is no chemical reaction that I can perform to break down these carbon atoms any further. You are probably aware of the periodic table of elements. We have all seen this large chart or poster hanging in nearly every science classroom. The periodic table is how scientists arrange all of the known elements. If you remember, a period is the time required for a wave or oscillation to repeat itself. How does that apply to the table of elements? The key is in that word repeat. Atoms are organized on the table by repeating physical and chemical properties. The properties reoccur periodically. This is a phenomenon you will see for yourself over the next few days. Today we're going to talk about the mastermind behind the modern version of the periodic table. That would be the gentleman pictured right here, Dmitri Mendeleev. Now, Mendeleev was not the first person to recognize trends in the properties of elements. So I would like to take you on a whirlwind historical journey about the concept of the periodic table. You could say this all began with Antoine Lavoisier, a French chemist that organized the 33 elements known in the year 1789 into two categories, metals or nonmetals. Not much of a periodic table, but at least it was an attempt to organize and classify elements. Lavoisier was quite the Frenchman and a fantastic scientist. It was his work that led to the law of conservation of mass. However, when the French Revolution began, he found himself on the wrong side of the uprising. It probably didn't help that he was cheating the government out of money and watering down tobacco. Lavoisier was beheaded as the new French Republic attempted to move on from a monarchy. Approximately 30 years later, the German chemist Johann Dobereiner noticed that some elements could be placed in groups of 3 based on their similar physical and chemical properties. These were known as Dobereiner's triads. Take a look at lithium, sodium, and potassium. They have similar properties. And look at this. If you average the atomic weight of lithium and potassium, you get the atomic weight of sodium. 7 plus 39 divided by 2 is 23, the atomic weight of sodium. Dobereiner recognized these same trends for calcium, strontium, and barium, as well as chlorine, iodine, and bromine. Interesting stuff, especially when you look at the modern periodic table and realize these elements are still grouped together. Here's another one of Dobereiner's triads. Use his triad concept to calculate the atomic weight of selenium. Pause the video and try this out. Now, fast forward about 45 years to the 1860s. This is when a method of classifying the elements really starts to take form. The number of known elements had increased dramatically, and more repeating trends became noticeable to scientists. The Frenchman, Biguier de Chancoiseau, actually published a 3-dimensional arrangement of the elements that resembled a screw. He placed the elements in order of increasing atomic weight and twisted them around like the threads on a screw. Elements with similar properties would align vertically on the screw. Very interesting. John Newlands took a slightly different approach. You could even say a musical approach. He developed what he called the law of octaves. Newlands observed that when the elements were placed in order of increasing atomic weight, the physical and chemical properties seemed to repeat every 8th element. Also, very interesting. Another scientist working on a classification system for elements around this time was the German chemist Lothar Meyer. He suggested several periodic tables, all of which were again organized by increasing atomic weight. Meyer was the first to recognize trends in additional physical properties of elements. Notice the repeating trend that occurs on his graph of atomic volume versus weight. As the atomic weight increases, the size of the atom increases, then suddenly decreases before increasing again, and then that pattern repeats itself once more. Now, Beguier, de Chancourtois, Newlands, and Meyer were all working on a periodic table around the same time as Mendeleev. Their tables were based on the same properties as Mendeleev's. They all placed the elements in their table based on increasing atomic weight. And they all grouped the elements on similar physical and chemical characteristics. So why does Mendeleev receive most of the credit for developing the modern periodic table? Most textbooks don't even mention these other scientists. Before we answer that question, I would like you to look at your periodic table. Start at hydrogen and scan the table left to right, top to bottom, looking at the atomic weight. That is the number in the box that has decimal places. Can you find 2 instances where elements are not arranged by increasing atomic weight? In other words, where the atomic mass decreases going left to right across the table. Pause the video and find 2 instances of this occurring. Okay, next I want you to remember the definition of atomic number. Pause the video once more and write down the definition if you can. Remember that the atomic number is what makes an atom of each element unique. If the atomic number is 6, I know that is an atom of carbon. If the atomic number is 55, I know that is an atom of cesium. So why on earth did every one of these brilliant scientists organize their periodic table by increasing atomic weight? The electron was discovered in 1897, and protons and neutrons weren't discovered for another 20 years after that. Mendeleev published his table in 1869. These scientists were working on the assumption that atoms were the smallest units of matter. They had no idea that atoms had smaller parts and absolutely no way of knowing that one of those smaller parts, the proton, would provide the solution for how to properly place elements in the periodic table. All right, back to our question. Why does Mendeleev get most of the credit? There are 3 reasons. First off, he was willing to make adjustments to his table for elements that didn't fit observed patterns. For instance, Mendeleev observed that iodine had similar properties to chlorine, fluorine, and bromine, and that tellurium was more similar to oxygen, sulfur, and selenium. Even though tellurium had a larger atomic weight when compared to iodine, he swapped their positions to fit the observed similarities. Secondly, Mendeleev left spaces in his table for elements that had yet to be discovered. And then he predicted the properties of these undiscovered elements. For example, he correctly predicted the physical and chemical properties of gallium, or as he called it, Eka aluminum, meaning the element one below aluminum on the table. This table compares Mendeleev's predicted properties to the actual properties. You can see just how spot on he was with his predictions. You can bet his contemporaries were fairly impressed with his work and were beginning to be sold on the idea of his periodic table. But the discovery of the element argon threatened to throw a wrench into Mendeleev's amazing classification system. Atoms of argon were totally unlike any other element known at the time. Argon was extremely interesting because it was totally unreactive. Mendeleev didn't predict that an element like argon existed, and argon had no place on Mendeleev's table. Mendeleev's initial defense was rather simple. Well, argon isn't an element. The isolation of helium gas destroyed that argument. Remember, spectral lines are ways for scientists to identify elements because each element produces unique frequencies of light when they get excited. After observing the spectral lines of the sun, scientists were quick to isolate a new element, helium. Helium was completely unreactive, just like argon. Mendeleev couldn't passively argue the discovery of helium. Helium was definitely an element. Was this the end of Mendeleev's periodic table of elements? Before we get to that question, just a quick review. Do you remember what is causing the lines of color created by excited helium and hydrogen gas? Pause the video and try to write down your answer. Red light for you, red. Okay, I swear, if I jumped off chairs and countertops for no reason, I will be severely disappointed. When electrons move from a higher energy state to a ground state, they release energy in the form of light. You remember that, right? Luckily for Mendeleev, his table would not only withstand this test, but be completely vindicated by the discovery of these elements. Over the next few years, 3 more inert, which means unreactive, gases would be discovered. Mendeleev was simply able to add a new group of elements to his periodic table. The noble gases all share the physical characteristic of being gases at room temperature and the chemical characteristic of being completely unreactive. Now we should know that the modern periodic table is arranged by increasing atomic number, not increasing atomic weight. The young physicist Harry Moseley was the first to determine this during experiments with X-rays. This was a significant discovery, and one that verified Mendeleev's swap of tellurium and iodine. The work of Harry Moseley is what led to the atoms on the periodic table being organized by increasing atomic number. Unfortunately, 2 years after this discovery, Moseley was killed in action during World War I. I hate to end this video on such a down note, but I think I've carried on enough about the history of the periodic table of elements. Until next time.